Hello, everyone. Want to welcome you to Agricultural Genomes to Phenomes Initiative Workshop. There are going to be people joining our meeting as we're going through our introduction. But I just want to let everyone know who may not be familiar with AG2PI that the overall goal of this initiative is to achieve sustainable genetic improvements of agricultural species. And this is being done by engaging a broad set of expertise and communities of agricultural researchers from both crop and livestock communities. This project has been running for about 2 years, and we are very happy to announce that we've received another renewal. This renewal is going to be dedicated to new seed grants at a larger size than what had previously been funded. For those that are interested, please feel free to sign up for our email list and watch for future announcements for when proposals will be coming due. I also want to let people know that there will be a survey that pops up when you leave this Zoom meeting, and we deeply appreciate you taking the time to provide feedback. There are only 3 questions, and it shouldn't take you very long to finish, but we use that feedback in order to help guide both AG2PI and our future workshops. I'm very happy to introduce today's workshop presenter, Dr. Arkantolis. He received his PhD from Wageningen University in the Netherlands in 2011 in crop modeling and physiology. He has been a professor in the Department of Agronomy at Iowa State University starting in 2014. He has won numerous awards, including the Pioneer Hybrid Agronomy Professor. He's a faculty scholar at Iowa State University's Plant Science Institute. He's received numerous early stage researcher awards from ISU, from FFAR, and he has well over 100 peer-reviewed publications. And I'm also very happy to announce that he's going to be a recipient from the American Society of Agronomy as a fellow. This is soon to be announced, and we are very fortunate to have him with us today. His research seeks to understand and model genotype by management and environment interactions, and really to help identify the best practices to move forward with the efficiencies in modern agronomic and agricultural systems. And his approach combines both field-based experimentation along with predictive modeling. His talk today is going to be focused on a system called APSIM, which stands for the Agricultural Production System Simulator. And this is designed to simulate biophysical processes and agricultural systems, particularly as it relates to economic and ecological outcomes of management practices, incorporating such things such as climate risk. And so he's going to focus this workshop on how to do the predict, explain, design approach to identify profitable and sustainable cropping systems using the APSIM as an example. And I just want to let people know that this workshop will run for about 2 hours or so. Over that time, of course, it's great to get people's feedback and questions. For this particular talk, Dr. Arkantolis has requested that if you feel like interrupting, please do so. You can try to get a word in, you can raise your hand, or you can go ahead and type your questions in the chat, where I will be happy to either interrupt or to wait for an appropriate break. This talk is going to be broken up into 5 major sections with pauses after each sections to get any questions any of you may have. And we strongly encourage and recommend that you do take that opportunity to extract as much useful information as you can from today's speaker. And so with that, Dr. Arkantolis, I am happy to hand the presentation over to you, and thank you so much for your time today.
Eric, thank you for the very nice introduction, also for the invitation. Very pleased to be here and talk about the APSIM software. And as you mentioned, I have split my talk. Actually, it's going to be a very long talk. It's going to be 2 hours. And I split it into 5 major topics. So what I will try to do is I will give you a big overview of the APSIM software. I want people to get a better understanding of what this software can do in crop science, plant science, and different spaces. So I will start with a big picture overview. Then I will go into crop modeling, and I will give some principles how the crop models are working. I believe this is very, very important. Many people consider these tools like black boxes. I want to open it a little bit and get your question, answer, and give more insight what is behind a crop model. The next one is going to be what I call the fun part of this presentation. I'm going to give you a demonstration of the software. You will have the opportunity to see how the software looks like, not only the beautiful results with the color lines, everything. You will see how we do the simulations. And actually, we are going to run a few simulations together. And so you will get more insight how to run simulations. And in this topic, I have listed here 7 quite common questions that I receive when I present modeling, like what are the input requirements? Does the model capture uncertainty? So I have prepared some slides about this, and we will go into details. The number 4 is about model applications. I will give you some examples, published journal paper results, and I'm going to talk more about what is the potential of using crop models in the agriculture space. And I will finish my talk with some useful websites where users can go and get help and solve problems when they are working with APSIM. So we have 5 topics, we have 2 hours, we have lots to cover, and I will appreciate if you have questions, please interrupt me while I'm presenting, and I will be happy to answer and have a discussion on your question. Now, before we start, I want to ask you, I want to guide a little bit your interest. I want to ask everyone to type in the chat the number 1, 2, 3, 4, or 5 to see in which of the 5 topics I should put more emphasis. I want to see a little bit your interest. Don't have 6. I think that's enough. From a quick data analysis here, seems like the number 2, 3, and 4 are the most important. Okay, so we will put more emphasis over there. 3.6, not 6. 3.6, how to extract the results. Perfect. Thank you so much. Okay, let's deal with the first one very quickly. The APSIM in overview. Okay. It's APSIM. The acronym stands for Agricultural Production System. As an advanced system simulator, predict can model the system performance over time with an equal emphasis on crop aspects and soil aspects, including soil organic matter, greenhouse gas emissions, and nitrogen leaching, all the environmental aspects. And what is very important about APSIM is that the management capabilities through user-friendly scripts, we can define all sorts of different management practices and simulate the effect of management on crop production and environmental performance. APSIM is an open source. Here is the website where you can go and see everything, data, code, everything behind the APSIM. It's free for public good and for research development and education. and there are some options for commercial uses. The development and maintenance is underpinned by rigorous science and software engineering standards, and APSIM is managed by the APSIM initiative. A little bit history. On the left, you see a picture with Greg McLean presenting at the International Crop Modeling Symposium. It was early 2020. It was the last event before the pandemic. And there is a nice summary slide over there where it shows the history of APSIM over the last 30 years. APSIM started as a cropping system model, then evolved into a farming systems model, and now it is an agricultural systems model with many crops, soils, and I will go into details later. There are 7 members in the APSIM initiative: CSIRO, the state of Queensland, University of Queensland, AgResearch, University of South Queensland, Iowa State University, and Plant and Food Research from New Zealand. It's a steering committee which guides the strategic direction of APSIM. And there is another committee, we call this reference panel, which is in charge of the science and engineering, quality control, and maintenance of the whole software. This committee is meeting once every 2-3 months to keep up with APSIM. In terms of usage of APSIM, is growing year by year. You can see a snapshot of what is happening the last 10 years. And at this point, I want to tell you something important. There are 2 APSIM versions, the APSIM Classic and the APSIM Next Generation. The APSIM Classic is how APSIM started, and then in 2016 it transitioned to a new software. I'm going to say more on that, which is called Next Generation. Both models are available for users to download, and as you can see, the Next Generation is taking off in terms of downloads compared to the Classic this year. And of course, the numbers are going to increase. The distribution of users are all over the world. With the dark red color here, it means more users. Couple of things about the APSIM Next Generation, which I'm going to focus a lot my presentation today, and the APSIM Classic. The reason for the development of the Next Generation, so what's the benefits of the Next Generation APSIM? First, it's across platforms. You can download versions for Windows, Macintosh, and Linux. It is faster. It has more flexibility. If you do a mistake, you can go back. We did not have this flexibility in the past. Much easier to build models and to update models. There are some very cool new features to get your own soil and weather data. There are some post-simulation sensitivity tools, optimization tools within the software. It has better science, modern software, and it is easier to create and sustain graphs. And also there are some factorial capabilities. The other version, the Classic, it has more crop models and other types of models, and has been tested over the last 20, 30 years. And the last release was in May 2019. APSIM Classic, there are no major releases anymore. All the emphasis is going to the Next Generation. APSIM is a plug-in pull-out module. So it is the user who is gonna select the management, the crops, the rotations, the years, everything, and build the simulation. As a big picture, there are 20 plus crop models in the Next Generation. In the Classic, there are more. There are annual crops, perennial crops, tuber crops, trees, and grasses. There are intercropping capabilities, and you can simulate weeds. Actually, any crop can serve as a weed. And there are models for animal. Okay, that was my very brief overview of the APSIM. Do we have any questions in the chat? Let me check as well. No.
Wait, it looks like we have one question from Daniel Kick.
Hi, yeah. So looking at the GitHub repo, it looks like there's support for at least one language, the APSIM on R. Is the idea to ultimately have APIs for different scripting languages to all access APSIM X, or are you preferring users to go directly to that and build out sort of extensibility layers if that meets their need instead of supporting it natively?
Well, that's a great question. So I think that's Dean Holsworth, the most appropriate person to answer this one. I know that you can go and grab all the code and everything from the GitHub. And I know recently they built functionalities through API to access APSIM and run it. But I have not done much in that space on that.
Gotcha. Thank you.
Thank you.
There's another question in chat. Is there an interface difference between the classic and next gen? Or maybe that's going to be addressed in section 3.
This is a great question. It looks about the same. So the structure, I'm going to cover this a little bit on the section 3. The structure are about the same, just it is much easier to develop graphs within the user interface, much easier to import measured data and visualize measured versus simulate data. In terms of the simulation tree, the structure are about the same. Both have management toolboxes, are very, very close.
Another question in chat. Are there plans to add the SWIM or SWIM soil water model in APSIM's next gen?
Yes, this is coming very soon. Actually, coming Monday, we have a reference panel meeting to review the SWIM 3 model for inclusion in the APSIM next generation. It is there. It's just a matter of time to review the science, everything behind it, and then it will get into the release process. Something important about the release process, I forgot to mention, it's a major difference between next gen and classic. There is a continuous release. So once we have a new model or an improvement, the users can download the new version the day after or 2 days after. While in the classic, there was only 1 or 2 releases per year. So people had to wait. So the answer to the SWIM question is very soon it's going to be there.
Great, thank you. Doesn't look like there are any more oh, wait, sorry, one just popped up. Another question is, are there plans to integrate DSSAT and aquacrop and other crop modeling tools into APSIM? Sorry, keep pronouncing it.
I don't know. I don't know this the answer on this one. You know, models. People run models. Many models, but I don't know if this. We will see. Let me say it like this.
I guess a follow-up question then that I would have on that is, do you have plans or is there support for the ability of people to plug in their own models or add other people's models into your system easily?
It's a great question, actually. I think there is capacity to do that. And we will go a little bit into details in the section 3, because there and also in section 2, I will show you some principles how we develop models within APSIM. But there are so many other different models. And APSIM is an integrator. It's a platform. Yes, you can bring in new models within APSIM.
Fantastic. And I think that helps answer the next question, which is how could APSIM be different from other existing models? And I think that's the difference between a platform to integrate models versus just another model. Not to say that any of those models are just another model.
That's a good question. And, you know, I received this type of question, why APSIM or why another model, etc. My answer usually is, it's like comparing two vehicles, two cars, BMW versus Mercedes, which is better. And so it's all the models have strengths and limitations. And I like personally to see lots of different models out there operating and learning from each other.
Great. I think that answers all the questions, and you're free to move on to section 2.
Okay, now we are gonna get a deep dive into the crop physiology and how we build models and how the model works. Let's try to open the black box now. Okay, let me start by showing you a kind of a list of crop models available within the APSIM next generation. This is the left column. This list is incomplete. Probably I forgot something. The list is continuously updated. It was June when the canola model or the mac bean model get into the release version. The classic model has more options, and there are lots of work right now going on into expanding the next generation crop models. Each model comes with a documentation. You can see here the web link. You can go and click on the PDF and see the science behind the model. So a model to be released within APSIM, it has to have a documentation. This is a must. There are many crop models, but to simplify things, and there are some kind of templates, generic templates. In the APSIM Classic, there was a generic crop template to build new models based on similarities among crops and species. And in the APSIM Next Gen, there is a new framework, PMF, Plan Modeling Framework, which is used to build new models. And of course, many models share lots of functionality. Now, the benefits of moving from Classic to Next Gen Plan Modeling Framework, we have a visual creation of crop models. We can reuse the code, flexibility in model structure, much faster building, and software and live science lessons integrated from the past. And in this paper, there are, and some other papers, there are some, how to say, points from the main developers, and I really like this, and I want to present here the lessons that they learn over 20, 30 years of model building is don't reinvent the wheel. You can't teach old code new tricks, and modern languages were developed for a reason. Keep it simple, smaller, simpler code, usually execute faster. These are great lessons, and we need to keep that in mind. Now, structure. On the left, you see the structure of the maize crop model. In the middle, the structure of the wheat crop model. And on the right, the structure of the soybean crop model. So you see there are some words that are repeated in every single crop model, although we are talking about different species. So every crop model has a phenology module. Every crop model has to specify the different plant tissues, like the grain, the root, the leaf, the stem. And of course, it changes, like in soybean, we have nodules. So it's up to the user to define the different pools of the biomass over there. And within the next generation, it is up to us to define how many we want to see and how much detail we want to include into a crop model. Now, there is a arbitrator. This is kind of not common. but this is very important component of every crop model because within the arbitrator, all the main actions like water uptake, demand of water, everything is decided within rules that are within the arbitrator. And of course, every crop model comes with a folder where we have all the cultivars. The arbitrator, it's complicated. I cannot explain it within a minute. Just the big picture. We have the mid-level classes like the phenology, the biomass. Then we have subclasses within the phenology or within the leaves. And then we have the equations. These are the functional classes. These are all the equations and the parameters that we try to optimize or calibrate when we move the model from one region to another, or we have new varieties. A little bit example, we have the phenology, and then we have the subclasses there. So the phenology is split into different phases, and each phase has some threshold values, and progression of the plant from one phase to another is mostly driven by thermal time, where basically the air temperature, and then we have the accumulation of thermal time. This is kind of a biological clock for a plant. It accumulates temperature until it reaches a certain threshold where it reaches, that's the end of the life cycle of this season for this particular variety. And this is from the user interface, and you can change this function. You can type different numbers and get different sort of relation here. It's very flexible. That's another one for the maize leaf photosynthesis. This is how it's showing up in the model. This is the actual equation, how it works, the model. We have the photosynthesis is the product of radiation use efficiency, the radiation interception, and then we have limits for temperature, VPD, nitrogen, water stress, and CO2, because all of these are affecting the photosynthesis. I will skip the soybean example. I don't want to get into too many details, but I wanna spend some time here. Does a crop model work? 4 very simple principles. What the model does. On day 1 of the simulation, the model reads the user inputs and the crop cultivar parameters. The day 2, the model calculates how many days we have to grow. The step 3 is to estimate how much dry matter through photosynthesis the crop can take up. And then the last step, it partitions the dry matter that came through photosynthesis into different organs, the stems, the leaves, and the grain, which is the most economic important for the majority of the crops. On the how many days, the model calculates the duration based on temperature and photoperiod in some legume species. In some models and in some cases, there are stress factors like water stress. There are some delays or acceleration in phenology. And another major factor on the how many days is the cultivar parameters. It's a question?
I'll find that mutant, but while there is a break, someone did write a question, which may be at the wrong level for what you're presenting, but the scientific equation for intercropping in APSIM X called MET is not clear. Could you explain it more? And I have to say, I'm not familiar with exactly what that means. Let me find the to mute.
Andy Masood, please mute. Andy Masood.
I think I did it.
Thank you.
Please repeat the question. I'm not sure I get it right. It was about intercropping, but I missed the second part.
Oh, sorry. The question is intercropping in an APSIM X called MET is not clear. Could you please explain it more?
Exactly sure about this. Probably that's something we can follow up after the workshop about the MET.
Okay, perfect.
Okay, thank you.
There's another question, which is, are there equations to calculate the genetic coefficients?
We will go on this. This is section 3. We will have a long discussion about this.
Perfect. Thank you.
Questions? Okay, so we are on the how many days and a few more details here. I will give you one example. This is how the model understands where we are. So step 1 is we tell the model when was the planting. In this case, it was May 1st. After that, we have the germination, the emergence, floral initiation, flag leaf, start grain filling, maturity, and harvest. From germination to emergence, this is an emerged property of the model. The model will tell us when the crop is going to emerge. And this is based on equations that include temperature and some depth relations. From emergence to floral initiation, this is a cultivar parameter. We have to tell the model what is the thermal time interval for this. For the next phase, the model calculates the flowering time based on phylochron and a number of parameters over there. Then another one that is user specific, thermal time from flowering to start grain filling, and another one to maturity, and that's it. The model calculates everything on a daily time step. So basically what it does is every day accumulates thermal time, target is reached. Once this target is reached, it starts to the next phase where we have the accumulation. Let's say this is the target, and that's all. And then it keeps going to the next phase. And within the model, we define the parameter values. We will talk about this in the next section. This step is very important. The next one is how much can accumulate within a day. And the black line, what you see here, is the daily crop growth rate. There are, let's go here around mid-season, around flowering time. There are days where we get 45, there are days we get 20. There's quite some ups and downs over there. And for us to understand how the model works and why it generates these ups and downs, we can see through the model everything that is behind the daily crop growth rate equation. One is the radiation use efficiency. This is kind of the actual. In this type of simulation, the orange line, there was no stresses, so it was a fixed number, didn't change over the season. However, the radiation interception, it was quite variable throughout the season, and probably this generated the variance in the crop growth rate. The radiation interception is the product of leaf area index, this green line here, and radiation, what is coming out of the environment. And by inspecting the green line and the blue line, obviously, the variability in daily crop growth rate mostly comes from the variability in the environment, in the radiation. We have cloudy days, we have sunny days, and biomass production is driven by light harvesting. So these are some fundamentals behind the crop models. Now, let me go back to this daily crop growth rate. We can integrate this one and get a sigmoid curve, which is the biomass production. Usually, researchers collecting some points here, and then we see how well the model does compared to the measurements. That's for later, but let me tell you this. Once the model estimates the total biomass production, the next step is to partition this one into the different organs. We have the leaves, we have, this is the grain, this is the stem, and this is the roots. Depending on the crop model, you may have different portions here, but the concept is you have the total and then you split it in different organs. Now, the splitting of the biomass is mostly done within the arbitrator. And there is an excellent paper that I recommend people to read, a generic approach to modeling allocation and redistribution of biomass to and from plant organs. And this is how APSIM works. If you want to get more details, I will refer to this paper. Now, it's a complex model. It simulates potential production, but is also simulating water limited and nitrogen limited production. To get to nitrogen and water limited production, we have to model water balance and nitrogen cycling. And then through some supply demand functions, the model estimates water stress and nitrogen stress. I provide here two examples, but I will not go into details unless participants have questions on this one. The general concept is that within the model, we define some stress factors, either for air temperature on photosynthesis, or nitrogen on photosynthesis, or water on photosynthesis. And the stress factors are usually different for different plant species, but assumed the same for all the cultivars, unless we have detailed information to develop different stress factors for different cultivars. And this is everything. Everything can be defined within the user interface of APSIM. Very simple approach to describe what is a crop model, the 4 different principles. There is way more science behind it and more complicated story, and long, many pages of equations and parameters there, all science-based, the majority of them. And the model, before it comes to release, it has to pass some validation data sets, including some training data sets. And I will show you a few slides to see how APSIM performs across different regions in the world. This is the soybean model. There are lots of different data sets from US, from Australia, and from China. And these are predicted observed flowering time, maturity time, biomass, nitrogen accumulation, the yield, and evapotranspiration, which in this case are pretty good. And these are, people can get this type of graphs and simulations from the GitHub. A different type of validation is time series data, which are very much needed for development and testing crop models. This is a treatment with early planting and late planting from Iowa for biomass, leaf biomass, the stem, the pod, different types of plant tissues. For the maize model, there are different data sets, and again, every model has to pass a validation, has to have a validation data set and show reasonable performance. And of course, each graph comes with a bunch of statistical indices. But the most important, what we pay attention is to not have a biased model. Now, let's download a version of APSIM, and then we try to test the model in our environment or different environment, and we do what I call post-validation tests. And this is an example using corn soybean data from Iowa. The points are the measurements and the lines are the simulations. This is a corn soybean rotation, typical for central Iowa. And at the same time, we test the soil nitrate and soil water. I was pretty happy with this type of results that I got from the model. And was the end of topic 2, and we'll be happy to take questions here on crop models theory.
So yeah, there's a couple in chat. The first question is it possible to use APSIM for coca crop?
So
Or cacao?
that's a good question for Neil Huth from Australia. Probably he's working on something similar. I don't know. There's so much development going on in APSIM. So many scientists working.
I think it's a great answer. And so follow up for that, is there, I don't know, a listserv or a place for people to post questions or do community building around these technologies, and specifically APSIM?
Yes, there is. And in the topic 5, user support, I have there a couple of websites, but mostly over the last 3 years, 4 years, we moved everything into GitHub, where people can go and see which models are under development, which one are to be developed, which one are we fix things or we improve things. And through GitHub, users or people who want to learn more, they can open an issue and post a question. Then someone within the APSIM community who knows the model is going to provide the answer. And the beauty of this system is that sometimes users reply to this post and exchange opinions and build collaboration. It's beautiful.
That is
everything is happening through GitHub. It's open access.
That is wonderful to hear. And I know one of the things that I do when hiring people is look at their GitHub repo, as well as the contributions, questions, and issues that they're asking of other projects or answering in other projects. So for anyone here who is an early career researcher or student, just keep that in mind. So with that, let me move on to the next question, which is, once we provide the cultivar specific information, do we need to come back to all the submodules such as phenology, leaf to initialize the values? Furthermore, when it comes to growing degrees days for any specific cultivar, I believe that those are region specific. So what are your thoughts on using them uniformly across all the places for modeling?
Yeah, great questions. Let me start with the second one. The cultivar phenological parameters related to thermal time, not calendar days. And we do that so people can use a cultivar from Iowa to Brazil or to way different environments, because it's a thermal time. Once you move a cultivar to a different environment, the cultivar is going to be the same. The weather and the soil is going to change, but the thermal time should be about the same. So this is how we go around about moving cultivars in different environments. Everything is based on thermal time. About the model initialization, the user doesn't have to do any initialization of the cultivar parameters. When it comes to day 1 values, there are some very small values, and I'm telling you, 100%, there is no genotypic variance over there. When the plants are babies, are all the same.
That was great. So as a follow-up question on that, do you have to rerun the models again and again to check and see the effect of any specific activity throughout a growing season? And I'm assuming that a parameter variation is what they mean by specific activity?
To get around specific activity, is this what does it mean by specific activity here? It's a management operation, it's a weather event, it's you change something in the model?
Yeah, Harsh Pathak, you're the one that asked that question. Maybe you can type into chat what you mean by specific activity. He's saying management activity, so I'm thinking something like fertilization. Fertilizing, sorry.
So look, you run the model requires all the information. So if you do not have in-season nitrogen application, then you have two options. Either you ignore this information and you perform the simulation, or you approximate a value to inform the model in order to complete the simulation with in-season application. Once you get the real data, when was applied, how much, yes, you have to rerun the model and get the prediction, the simulation. Of
Perfect.
outcome with this action.
So, excellent. Another question is, do you need daily weather information to infer the amount of radiation on each day? So yes on that one.
Yes.
Another question is, what are other major data needed to run APSIM?
Okay, we will go there. It's next topic.
Next topic, perfect. There's a detailed question called, how can I create a MET folder? And I'm not exactly sure if this is appropriate for here or if that's something that might go to GitHub. I'm sorry, Rami, if you're the one who is chiming in on that, you're breaking up.
Eric, is the 3.5, we will cover this.
Okay, perfect. Another question is, does the model consider the variable nature of canopy extinction coefficient, parentheses, changing nature of leaf angle throughout the growing season when estimating the proportion of radiation intercepted? So basically, does your model account for leaf angle changes over a growing season?
That's a great question. So look, in the classic, there was nothing over there. It's only with the row spacing, the extinction coefficient is going to change. In the next gen, in some models, there is a temperature, there is a moisture stress, which can change the light extinction coefficient. When it's very dry, the leaves start rolling and intercept less radiation. This is part of the next gen. So this can introduce some change in the light extinction coefficient and architecture in the canopy.
Perfect. I'm just going to take a look to see if there are any hands up for people who do want to ask a question out loud, or give people just a couple more seconds to type in a question on this section. With seeing nothing, let's move on to the next section. Thank you.
Hey, thank you, Eric. Thank you for all the help. Okay, the next one is a demonstration of the APSIM user interface. Instead of pulling out APSIM and start running simulations, I took the safe way and I did screenshots. I did some simulations yesterday to make sure we don't have surprises. Sometimes APSIM and Zoom doesn't cooperate well. Okay, so this is a very, very important slide. This is the model. What you see here is the model. Ignore the graph. The rest is the model. This is the APSIM user interface and looks quite similar to Microsoft Word or Excel, where you have this option save, save as, undo, redo. And this is the most important one. This is how we execute the simulation. Now, we have a navigation bar here. This is the top navigation bar of APSIM. At the top, you see the release version. And on the left side, we called this portion the simulation tree. And a simulation tree consists of a data store, a database. All the data are stored over there. And this is a simulation, and the name here is corn example. We can give any type of name here. And this is the name of simulation. It's gonna be written when we output the files. And then for the model to run, simulation from scratch. We use an example or a starting point, and then we start modifying the existing simulation. If you click at the home button, in the APSIM user interface, you get to a second navigation bar where you can have a folder with the name Open an Example. And once you click here, you come up with a list of many different simulations. You see which one is closer to your case. You hit click, you bring the simulation in, and then you start modifying weather, soils, etc., and management in order to build. And there are many other helpful tools here, like you have a bunch of crop models to select and bring into the simulation, management options, some training simulations, and this is how we upgrade the model. We click here and the model does the rest. It asks which version do we want to get, and it is very easy. They have made APSIM so easy to upgrade to a newer version. Now, let's go back to the simulation tree. We talk about weather, we talk about how to bring in some new simulations, and I'm going to explain some other components. The next one is the clock. This is how we tell the model when to start and when to end a simulation. It's very simple. And in this case, we are going to run the model for 1 year, 365 days. The next one is to tell the model which crop you want to simulate, when it's planted, which cultivar, and you see here in the cultivar, this is a 105-day hybrid. And if we click here, I cannot click now, you will see an option with 40, 50, I don't remember, existing cultivars within APSIM. Then the user has to specify some additional management information, and that's it. If you want to see the code, the script behind, you click here and you see everything. Or you can modify. It is very flexible. So planting date hybrid, very important to run a simulation. Then we need to tell the model to apply the amount of fertilizer to be applied. And in this case, we don't have an option to tell when, because this particular script is going to apply fertilizer at the time of planting. There are more scripts within APSIM where you can do split application, you can do on a fixed day, you can do based on thresholds when the soil nitrogen is below a threshold, then apply that much nitrogen. You can apply different types of fertilizers. There is quite some flexibility over here. So this is how we get the data into the model. The next one, before we run the model, is to tell the model what to give us. Like in this particular example, I want to see the above ground biomass, I want to see the leaf area index, the grain weight, the soil water in the third layer, and I want to see the minimum temperature. This is a major difference compared to the classic approach. In the classic model, APSIM model, there used to be a top-down menu where the user was going and selecting what to see. In APSIM Next Gen, the user can type the name of the crop model or the name of the soil model or the weather model, and when it hits period, then a pop-up menu appears and you have a bunch of different variables to select. So it's more typing, selecting here. It's very useful. It takes some time to go around it, but I found this to be very flexible. Bottom section, we have to tell the model when to output the data. Are we aiming for daily simulations? Then we use end of day. Do we want to see the results at harvest? Then we select at harvest. Do we want to see at the end of the year? We select end of the year. Do we want to see once per month? We tell the model once per month, once per week. There's quite some flexibility there. This is really, really powerful. Now, we have set up everything. We click, run, and then we have our first simulation complete. Let me start explaining here what we see by looking at the bottom left, this is the execution time. It took 0.49 seconds to run 365-day simulations on my laptop. And in the reports, the properties is what I showed you in the previous slide. And if I click data, these are the results. And there are 365 number of rows. Next one is to visualize the results. And the way we do that in APSIM is by doing right click, select a graph. I will not spend too much time. This is more in-person training, workshop, and practice. We bring a graph into the simulation tree, and this is how we build and expand the existing simulation. And then we start selecting data source, in this case is report. What do we want to see in the x-axis? Preferable time. Y-axis, probably yield, and then all the details of a graph. And once we select, we start seeing the simulations. And if we click on the graph, we see a big graph, which is very clear. And in this case, we see the maize grain yield in grams per square meter. It was 0.000. Somewhere here is the planting, but we don't have grains the day after. We have to wait until mid-July when it's flowering time. And then it starts slowly and then takes off, increasing a lot during grain filling period until it reaches maturity sometime mid of September. The crop stays there for a week, 2 weeks until the manager decides to harvest. So this is a simulation, and after we harvest the crop, the model is going to write 0 yields. So this is a simulation, and this is how we see the results within the APSIM. It's easy, straightforward, and enjoyable to run the model and immediately see the results. Now, let me show you how to run a 30-year simulation. We go back to the clock, and the only thing we have to do is to specify the start and the end day. So in this case, once we change the clock hit run, we have 30 years of simulations, daily simulations, because we ask the model for more data. The execution time in this scenario was 2.16 seconds. And I mentioned these execution times because there is another frequent question we get is how fast is APSIM? So I want to provide some numbers on that. Now, looking at the results, you see quite some variability from year to year. And this is with the same genetics. This is a kind of a G by E interaction here. We can make the simulation more complicated, and we can get the corn example and duplicate it one more time and have 2 simulations. And this second scenario, we don't apply any nitrogen fertilizer. And we can see the results here. The black is with 150 pounds of nitrogen. The orange is without any fertilizer application. And to me, these results make sense. It's an Iowa environment. I'm well familiar with that. So all good in this simulation. But mostly this is a kind of demonstration on how we run the model and we visualize the results. Now, someone asked earlier, and that was one of my frequent asked questions, how do we export the data? Okay, so once we click on the database, data store here, right click, we have a bunch of options, and we tell the model export data to Excel or TXT files, etc. And the model is gonna write an Excel file with the simulation name, the date, the name of the variable, another variable, everything. Every day is 1 row of data, which database can be analyzed by different softwares. a little bit my presentation by introducing the factorial experiments. Most of the cases, people using simulation models to replicate an experiment. And a common experiment is a yield response to nitrogen. There are several experiments with 5 nitrogen rates, one genotype, let's say like this, and we want to see whether the model can replicate that one and extend to different weather years. The way that we simulate experiments in APSIM is using the factorial option. There are, once we do right click, we have to bring in the experiment, and then we define the factors, and in this case is the nitrogen fertilizer. The user has to say what is going to change in the model. In this case is fertilization, and we want to vary the amount from 0 to 400 at a step of 10. This is how we tell the model to run a nitrogen trial every 10 kilograms, every 10 pounds of nitrogen. Once we run the model, we get 40 different points, and we can construct the nitrogen uptake to fertilizer application response, which is a nitrogen use efficiency. We can have the yield here. We can have any sort of variable. For your reference, this particular simulation, it was 40 treatments times 35 years, 1,400 simulated points, and the execution time was 4.9 seconds, using my little laptop. Now, let me show you more flexibility, and this is very much related to the title of the presentation, and lots of the work that we do in our lab is environment by genotype by management interactions. In the previous slide, I show you the experiment, which you can rename it to something else. Then you have the factors, but in this case, instead of having one factor, you can have 3 different factors. You can have as many as you want. There are so many combinations. Just don't overmake it in order to not have any model crashes, etc. Keep it reasonable. In this case, I highlight the genotype, and this is how we tell the model to run simultaneously many different genotypes. And different management is about the same as I showed you before. Once we run the model for many years, through the user interface, we can visualize the yield response to different maturity groups. Each different color here represents a different maturity group. And this color here, I think, is maturity group 3, Iowa, May 1 planting. This is exactly what we expect to see. The yield response to planting date for a maturity group 2. This is what we expect to see, and this is what the model gives us. So we are happy with these results. Now, in this case, I ran 264 simulations times 35 years, nearly 10,000 simulated yields. And in this time, the execution, the runtime was 4 minutes. So the more you ask from the model, the longer it's gonna take to generate the results. And also, the more output variables you ask the model to give us, the higher the execution time. So it's the execution time is variable. Simple simulations are extremely fast. More complicated takes more time. But again, the numbers here are based on my little laptop. Okay, so I want to go to many frequent asked questions like, how do I get weather data? How do I get soil data? How I do cultivars? And this is what we are gonna do in the next couple of slides here. But if there are questions, I know the section 3 is quite long. Please, Eric, I'm happy to make a pause here. And yeah, I see there is a question.
Yeah, I would say that's perfect. There's a lot of questions that have come in. Why don't we go to the person Harsh Pathak, who has their hand up.
Okay, let's go.
So Dr. Sotorius, I have like one quick question. So suppose if we are farming a particular land and we have done some activity, so without putting the harvest date, can we run the model to see like at what particular stage our crop should be or not?
Well, that's a good point, and thanks. That's a good clarification point to make as well. The date of maturity is an emerged property of the model. When it comes to harvest, it is beyond crop physiology or biology. There are lots of logistics. And the model will tell you when the crop is ready to harvest, will not tell you when to harvest.
So suppose so my question is a bit different. So I have planted the crop in April, and in June, I am trying to run the model to see like what should be the crop growth stage for now. So can we get that or not with the APSIM?
So you can, absolutely you can.
And without like putting the harvest date, I tried to run for one of the simulation and it was like it was not showing any results.
Get the results. If you don't have weather data all the way to the end of the season, you have weather data, let's say until July, the model is going to give you data until July, until the last day you have weather data.
Okay. Yeah, thank you.
So just as a sort of a broad question from Abibi, which is, they're basically working on their PhD and going to be using multiple models. And their question is, in your opinion, what's the best programming language? And they list two, R or Python for APSIM.
So that's a great question. I wish my colleague Isaiah Huber was here to give some more insight on this. So look, APSIM NextGen is mostly C# written. In the classic, there were many other different languages. I don't think I have a good answer to offer over there, but I can tell you, different models are written in many different languages.
I was hoping you would say Fortran. Next question is, how can we add new cultivars to APSIM that aren't currently listed within there? I'm doing a little ad-libbing on the question just to try to make it clearer.
Perfect. I will get to that in 3 slides.
Fantastic. Do you have a recommendation on the minimum amount of data that you need to run a simulation?
I do have a recommendation, and this is coming as well about the minimum data. This is a long discussion about the minimum data. We will do that.
Okay. Another person asks, how do you create an experiment or a simulation that has split application of fertilizer?
That's easy, and I will answer it right now, this one. I will get back to my simulations. Okay, let's see this particular example. Whatever is in blue here indicates a person. This is the manager on the left in the simulation tree. And you can see here the fertilize component. You can apply an amount here, and you can bring another fertilizer component and apply another amount at a later day. So that way you have 2 applications within a day or 3 applications within a day. And all of these management rules can be found within this management toolbox. Unfortunately, I didn't click here to make another screenshot, but users can go there, click, and then they will see a list of different fertilizer options. All they have to do is to take, if they want to fertilize on 2 particular dates, put 2 management components within the simulation. There are many other rules, or you can have one script and with comma, you can define the second application and amount.
So that's probably leads into this next question, which is, can you simulate different days for planting for any given crop? So similarly, like different start days, I assume, for the season.
I think this is to some extent covered by this type of analysis that I did. Where is it? Here in this particular simulation, within the management, instead of having here the cultivar, we say planting date equals May 1st. Oh, actually it's this one. April 1st, April 15, May 1st. So you can type all these values here, and the model is gonna simulate the experiment with different planting times. So yes, very possible. That's all doable within the simulation framework.
Great. Can we do it factor? Can you try to understand this question? But it's can you factor in different cultivars at the same time? I think is what the question is asking.
Yes, the answer is yes, and a demonstration of that is in this particular slide, where we tell the model to simulate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different cultivars.
Okay, great. Someone also asked a question on explaining the microclimate in intercropping simulation.
Microclimate, okay. So the microclimate, let's see, where is this one? The microclimate, okay, I didn't have a click here. So basically, over there, within the microclimate, the model calculates the potential evapotranspiration using the physical Penman-Mondith approach. And there are some constant variables there. And the microclimate, it is very important in the simulation because it can deal with different crop canopies. You can have two different crops in the same field. You can do all sorts of intercropping issues there. And this model, the microclimate, is going to decide how much light and which canopy is going to intersect. There is nothing for the users to do in the microclimate. There are some exposed parameters, I think 4 or 5, but we would say we have to change these values. It's a necessary component that needs to be in the simulation. And because we don't have to edit this unless we have concrete information, that's why I didn't brought it up as a slide. The most important we have to change in the model are these ones, like here, the amount of nitrogen, the timing, the cultivar, this type of things, and the weather.
Perfect. And then one final question, at least out of the chat, is how do you create spatiotemporal data using APSIM?
Oh, very good question. So look, there are many different ways, many different ways, and people have done it in different ways in the literature. So let me share some thoughts here. First, very simple way. You use the user interface as it is here, and you have a bunch of different soils, and you run the simulations for different soils, and every soil has 30, 40 years of weather data. So this is a kind of spatial and temporal data. The other one is to run APSIM through command line. You can run APSIM through R, through Python, you decide, and then you import different soils, different weather data, and the model converts that to many different spatial and temporal data. The other option, there are some other software platforms like the parallel system for integrating the inputs and models. Don't remember the name now, which gets lots of data, feeds APSIM, and executes hundreds, thousands of simulations and generates a NetCDF format. So these are three different categories and three different approaches that people use to generate the spatial and temporal data.
Perfect. Just to let people know, we have one more question. Feel free to type them into the chat or raise your hand. Question that just came in is when multiple simulations are being run, are these being executed in parallel so that whatever system people have, they can use as much of the resources as possible?
Yes.
Perfect. Parallelization is baked in. Fantastic. If there are no other questions, then thank you. Move on to the next one.
Okay. The next couple of slides are frequent asked questions. So I always receive this question. So I decided, okay, let's put some slides here to have it and people can go back and look. How do I create a weather file or many different weather files? Here is my answer. There are many different options. The best, I will talk also about the source of weather data. And the option one, the best source of weather data is local weather station data. So this is what people should have top in their list. And the data that APSIM requires is the radiation, the daily. This is kind also the minimum data weather requirements. Daily radiation, maximum temperature, minimum temperature, and precipitation. So this is what the model requires for every day. You get the data into an Excel and it is easy to get into the model. That's one way. Now, not everyone has weather data, so we have to go to a plan B. There are many gridded sources of weather data, and here I list the NASA Power, a product that we are using a lot for simulations, and people can go and download single point data or can use services and get lots of data, spatial data to input into the apps. So that's another source. And of course, NASA Power is one. There are many different gridded products out there. Now, let me present the third option, which is based kind of NASA Power. And this is something that APSIM users will like to see. So in the next gen, there is an option to make a right click in the weather component, and then you go and say download weather, and a pop-up window is gonna show up there. And all you have to do is to specify your region. It has to be Australia or world. And then you specify latitude, longitude. You give a name, that's optional for the address. Then you specify the source. There are different other sources. And then from when to when you want to get data, in this case, 84 to 2022. And then you click, of course, you point where you want the file to be saved and you hit OK. That's it. You have a weather file within 1 second. I'm telling you, in the past, before this functionality, it was taking quite some time to gather data, format the data, get it into APSIM. So this is a very good capability that has been added into the next-gen model. This is my answer to the first question, how to develop your own weather data. Now, the second one is how do you create a soil file? I didn't say much about the soil. This is a whole new workshop to talk about soils and parameters. And in the simulation tree, you have the soil, and under the soil, you have a bunch of components, physical properties, some soil water movement parameters, temperature, there is no parameters there. And then you have to deal with the organic matter, etc. There are lots of parameters there. There is an excellent publication which I listed here, and I will recommend APSIM users to go and have a look at it, because it is a very recent protocol that summarizes also previous experiences on how to build the soil descriptions for APSIM simulations. So basically, it proposed some techniques to get public data and convert it into APSIM crop model data. Keep in mind, that's very important, and I want to communicate this, that public soil databases were not designed for APSIM model use or other crop model inputs. Some conversions, and some model inputs are not measurable. The APSIM model requires organic carbon. Usually organic matter data are available, so we have to make a conversion there. And then we have to further split the data, the organic matter, into different fractions. So there is up to a certain point how many data we can get from public data sources or measurements, and then we have to make some extra calculations to estimate everything. And this paper go into many of these details, so I recommend users to have a look at this paper. Again, as in the weather data, the best option to get accurate soil parameters, which is extremely important, is to take soil measurements from your field. I will recommend a deep soil core, a few, not just one, and then estimate organic matter, texture, and pH, and all sorts of soil parameters. And then you start editing the APSIM file, where is the soil input parameters. If you don't have the resources or the experiment happened in the past and it's impossible to go back in time, and if your experiment is in the United States, I will go after surrogate data. And then the other one that APSIM users will like a lot, as a good starting point, I would suggest they use the APSIM new functionality. So what this is, you make a right click on your soil, and then you say download the soil. And here is one example. This is the latitude. This is basically Ames, Iowa. Once I click that, the model figure out where I'm located, and I click search for soils, and it gave me 4 different soil series. And then all I have to do is to highlight one of the 4 and say select soils to my simulation, and this particular soil will come here on the left. I delete the existing soil and I have a new soil. And I can see here on the table some of the parameters that are associated with different soil types. So this is a major time saver for many users, because generating a soil profile requires quite some time, resources, and above all, expertise. You need to know the model. You need to know the meaning of a parameter in order to come up with some descriptions of soil variables. So this is an excellent source for people to have as a starting point. However, I want to reinforce the importance of measuring the soil. Here. Cultivar. This is the number 3 question. How do I develop a cultivar in APSIM? Okay, so it is pretty much you have these components, the replacements at the top of your simulation. You have to bring a folder, name it replacements. Then you bring in your maize model, your soybean model, your wheat model, whatever model you want. You expand the model, you see all the structure. And when it comes to cultivar folder, there are going to be a bunch of different cultivars. All you have to do is pick one cultivar that is pretty close to what you expect and rename it. And in this case, here is the cultivar that I created this morning, AG2PI cultivar. And these are a number of parameters. So this is how we create a cultivar within APSIM. It's basically use an existing one, bring it in, modify numbers as needed, add more variables as needed, remove some as needed. This is the general concept. However, these numbers may not make lots of sense for everyone. What I wanna reinforce, what I will say, it's something more important. The message is that what we should measure in order to develop a cultivar, not just how to develop a cultivar in APSIM, because without data, you cannot develop any new cultivar. And I call this wish list. This is the ideal, the top data set that a modeler would like to have in order to develop cultivar parameters. And keep in mind, this data should come from experiments with no stress, with no limitations. How many cases we have access to this type of data? Very few. And this is a major challenge we have in the scientific community with the cultivar. We can develop cultivars with fewer data. And if we go to the concept of minimum data, I will go for phenology, biomass, and yield. But having more insight in season data, it is very much needed to develop this information. And sometimes, this is mostly for development, we need to have experiments where we measure response functions in order to develop the photoperiod sensitivity functions. Things can get easily complicated. But portion of my answer here is to demonstrate how you do it in APSIM and some concepts as you plan field season and measurements and what to measure and how to develop cultivars. That's what I wanted to cover here. And then another point, a very common question is about uncertainty. APSIM, as every crop model, is a deterministic model. However, you can fine-tune some parameter values, you can increase the range, and you run the model multiple times, and you can generate a kind of uncertainty. And you can add uncertainty in cultivar parameters or some soil inputs. There are uncertainty with the soil inputs as well. And then we can see the impact. There is a great tool, the Morris Global Sensitivity Analysis tool, and it can be used within the simulation. Here is how this tool looks like. And you can define lower and upper bounds and parameter values and see how sensitive the model is within a range. So this is one way to generate uncertainty. You can change the weather, it's up to the user. Now, briefly summary of data input requirements: weather, daily max mean temperature, precipitation, radiation, wind speed, and humidity are very welcome for next gen. They can be used if provided. If not, the model is gonna come around with these only parameters. The soil, organic matter, hydrological parameter and texture, surface slope, and initial conditions for water, nitrogen, and residue amount. And management information is planting date, density, nitrogen rate, and tillage, and cultivar. Because we don't have cultivars, there are so many cultivars. One way to go around the cultivars is to develop some generic cultivars. For soybean, we have generic cultivar maturity group 2, 3, 4, 5. And within this maturity group, there can be hundreds of different varieties. So there are some default variables there. So knowing the maturity range is very important. Okay, so Eric, in this third section, we covered lots of ground. You see lots of green points here in the red slide.
Yes, there are. There's a lot of questions. And I think the first question you've answered, but I just want to double check because it came out before you talked at length about soil parameterization. And the question is, what about soil moisture at sowing date? And it sounds like the answer is read the publication on public databases that are not designed for APSIM. And you made the comment of you need to go take your own soil measurements in your own field. Do you have anything to add to that?
A little bit. It will be fantastic if we have soil moisture at planting, but remember, we do not always start the model at planting. We can start the model a month before planting. What is most important to have is day one, what is the moisture, what is the starting point? If you start the model at planting, yes, we need at planting. But if you start it a week before or 3 months before, then I will prefer to have on day one.
Perfect. Someone asked a question about importing weather data in MET format and whether or not the program accepts quote unquote an Excel folder, which could be dangerous as Excel files can be any formats in there in terms of the columns.
So NextGen is quite flexible. I have seen people using Excel files and some other people using files with the extension .met, basically TXT files.
Okay.
So there are quite some ways to do that.
So as long as the Excel file is probably formatted correctly, in terms of the columns and rows, there's an import function for that. So another person asked the question of, do you have any opinion on the reliability of data downloaded from the NASA tower as compared to real ground data or ground truth data?
That's a good point. I will share my personal experience. I had the same question, and what I did was to download 20 different points from NASA Power for the US Corn Belt, and I gather local weather data, and I make the comparisons. To me, the prediction accuracy was pretty good. I was happy, and I'm using NASA Power in my simulations.
Perfect. Someone asked a question. Could you please explain the genotype in the crop model simulation?
Right. So I will not call it genotype. I will call it cultivar traits over there. There are no genes in the cultivars. The lowest level we deal right now is with the traits. And basically in the cultivar section, there are some parameters. The majority of the parameters are associated with the phenological stages. How long it takes from this stage to that stage, so we can fit the environment. And then if we know some changes in radiation use efficiency or transpiration rate or canopy extinction coefficient, then we can enter these values. But usually we try, we have, there is no general rule behind that. The phenological parameters are the ones that are mostly exposed and changed from cultivar to cultivar.
Great. Otherwise, you would have solved the genotype, phenotype, environment problem, right?
We have work to do to solve these problems.
All right. The last question that's in chat is, how can we get photoperiod sensitivity of the cultivar?
A nice experiment with different photoperiod levels and different temperature levels and different genetics will be fantastic. So we can get some data. This is one way. I wish I had this data. The other way is to have the same genotype grow in different environments from Canada to Texas across this region, and have these experiments run for a couple of years and then generate the data and come up with some analysis and photoperiod sensitivities. The third way, and usually people do that, is they have experiments with different planting dates. So they create different environments within an environment. Now, honestly, the best is if you have all these three. Let me stop my answer here. That's how we end up with the photoperiod sensitivity parameterization. If you have nothing of the above that I mentioned, just use default values for a generic cultivar. as the best you can do.
Perfect. All right, I'm going to see if anyone wants to raise their hand and ask a question verbally, as well as give people a couple of seconds to type in something into chat if there's more questions. Any questions from the audience? Please raise your hand. Nothing coming in on either side, so thank you. Just to give you a time update, we're at about 20 minutes to the hour. Very impressed with the engagement of everyone on this. I turn it back over to you.
Okay, thanks, Eric. The next two sections are, I will call it brief, so we will have more time for discussions. Model applications. There are many, and this is something that came out of APSIM. There are 1,300 publications associated with the software, a bunch of analytics here, and what I like, and everyone likes this number, is 88 index. That's pretty cool. So there are many papers out there, and the list is growing and expanding. So what I did in this section, I just gathered 3-4 published papers to show you some case studies. It's impossible to discuss more than this. So the first one is one from my own lab. We used APSIM to predict crop yields and soil plant nitrogen dynamics in the United States Corn Belt. We did this work with the APSIM Classic. It was a project from 2015 nearly to 2020, and then we gathered the results and we published. We set up close to 9-10 experiments in different environments in Iowa, are the points here. We had the objective to forecast crop yields as early as planting time, and then was to evaluate and improve the performance of the model. We collected the WIS list that I presented a couple of slides before, including soil measurements, not at planting, not at the start of the day, but throughout the growing season, using soil moisture sensors. And we collected soil nitrate and ammonium data over lots of data sets. Some highlights: we built also a website to disseminate the information in public. And it was a kind of a hybrid approach where we put in the website both measurements and simulations for the stakeholders to see how well the model can predict and build confidence around the use of crop models. Our approach was to use historical weather data up to a certain point, then to use forecasted weather data, and then an ensemble of historical weather data where we were getting the median. And we were releasing forecasts every week, every 2 weeks, starting at planting and updating. And we were convening all the way to maturity. And at harvest, we provided also the measured yield in the website. These were done for 3 years as part of a project, and the results were disseminated in real time. And of course, after the growing season, we were getting the in-season measurements, and we were improving the model to be ready for next year. There were a couple of iterations there, and we learned a lot of things. I will not go into very detail. Now, here are 3-4 key messages that I want to share with you. We learned that when we apply crop modeling and APSIM in the US Corn Belt environments, especially Iowa, Illinois, we need to consider the shallow water table. It's an important source for crop production. And this source of water is so important that can increase the yield up to 15-20% and stabilize the yield from year to year. And you can get the yield response to the yield response to precipitation much more accurate. This is one main reason why we found the median yield prediction at planting to be the second most accurate prediction after the prediction at maturity. So if you come to the bottom panel here, when we start the model, the uncertainty, which is mostly weather, of course, we have uncertainty because of the cultivars, is pretty high, and towards the end of the season is very low. But the error in the prediction was between 15 to 20 at our first attempt to predict the yields, and then increased, decreased, and that was the lowest we could get. So that's why we say prediction at planting is the second best after harvest. Also learned that the accuracy in management records is extremely important. It accounted for nearly 25% of the total sensitivity. And the other thing is that the inclusion of the 1 week weather forecast didn't help much. And June predictions, it was the most viewed by the users. After July or August, people pretty much had a sense of what is going to be the yield in their own fields. The highest demand for yield prediction was early in the season. Second example is with machine learning. So what we did was to use public data, machine learning models, bunch of different machine learning models to predict yield. And then what we did was to run APSIM across the states in the United States Corn Belt and outputted the variables from APSIM. And we used these variables as an additional input to the machine learning to predict the yields. Of course, we did testing of APSIM across the Corn Belt, and the model did well. This is kind of spatial variability of soil moisture simulations using APSIM. You can find these results in the public website. And what we learned is that the hybrid approach, machine learning and APSIM, has a better prediction compared to the classic only machine learning and public data. And that was true for many different machine learning models or ensembles of this type of model. So that was an important result. And I will skip this type of information. And the paper, you can go and see what we did. It's very, very recent. That's why I put it in. It's calibration of APSIM classic version 7.10 with 15 publicly available corn hybrids. So that was work that led by Cassie Wink and Jyoti Edwards, and I helped with this project. Cassie, during her PhD, collected some data. These are the points, and then she ran the simulations to create all the different phenotypes. And one obviously result from here is how nice is when you have a continuous line rather than just a few points here and there. And one important outcome from Cassie's work is that we ask the question, okay, how many data do we really need to calibrate the parameters? And what we found is summarized here on the left panel. When we have absolutely no data, we just use a previous calibration, different cultivars from a previous study. We have a normalized root mean square error of about 35. Once we start getting some partial information, basically phenology, then we start decreasing this error. And once we start getting all the information we need, like grain, nitrogen concentration, leaf area index, biomass partitioning, that is where we can get the error much less. Keep in mind, the error will never be below 10 to 12% normalized root mean square error. For different variables, the amount of data are a bit different. And also this is affected a lot by genotype. So that was something important we had to deal. And of course, we ran the model to generate G/E on different traits. Now, I shared some work from my lab, and I want to highlight two more very important publications. Pretty sure some of you have interest to know more about gene to phenotype modeling using crop models. And I will highly recommend have a look at this publication by Mark Cooper. I read this recently and really like it. Basically, the concept is you have a bunch of different genes, and this comes to a yield expression, but you can arrange this. You have the yields, the genes, which affect different components of the plant, like phenology, canopy development, biomass, partitioning. And then you have a bunch of different functions here which affect these processes. And at the end, all this lead to yield. So you add the model, the crop model, between the genes and the final output. It's a nice study to have a look and get more information on that. And the other one, again, published in the same journal, In Silico Plants, is about integrating crop growth models with remote sensing data for predicting biomass yield of sorghum. So that's the useful information for you to have. And that was my brief description of model applications. There are way more that I can talk about this. I think that I covered some areas.
I was like that is great. I know what might be useful as I'm answering these questions is if you do have like, you know, the PubMed IDs or links to those papers, you know, if you could put them into chat quickly while trying to answer questions, I think that might be useful for people, just because I deeply appreciate the resource that you're providing with that quick bibliography. But while you try to do that, you know, there's a series of questions. One of them is, you know, I work on field peas, and I see that they existed on APSIM Classic, but not NextGen yet. You know, how could I find out if someone is working on adding them to NextGen? I assume that's through posting a question on GitHub, but
exactly,
yeah.
Exactly. That's the fastest way. I would suggest the person who has the question to type it, create an issue and say, is any field P model or when it's going to be ready, something to post the question in GitHub.
Perfect. So Leas, I think there's your answer. Next question is, can APSIM predict greenhouse gas emissions from tillage, such as methane and nitrous oxide?
APSIM can predict greenhouse gas emissions, N2O and N2, but not methane and some other ones.
Perfect. What strategies or data sources do you recommend for simulating shallow water tables for applications where field measurements are not currently available?
The best way to measure water table is to install wells, deep wells within the soil, and then you measure every single day the ups and downs in the water table.
So if there's wells nearby or something like that, you could use it. That's a great thing. And then another person asks, can you explain the procedure or process for doing calibration?
2-hour workshop. There are so many things to say about calibration, but briefly, usually people calibrate the model around the measured data they have. What I will suggest within 1 minute here is that keep your changes in the model at a minimum. Don't change the model behavior. Try to calibrate things that are exposed in the user interface or traits that you know are quite variable. Don't change very, very specific things, traits within the model. And get advice from an expert when it comes to calibration, because it needs to keep a balance between soil and crops. And usually what I have noticed with various students is crop scientists, they are going to change only crop traits, soil scientists, only soil parameters. We have to keep a balance there.
Perfect. Perfect. All right. With no more questions and oh wait, one more question just came in, which is when you're looking at the parameters in the user interface, could you please provide examples.
Okay, examples. So it's in the soil parameter section where we have all these tables by layer about the field capacity, the saturation point, the wilting point, hydraulic conductivity. So all these parameters need to be updated for any type of experiment or environment we're going to run the model. So these values are exposed in the user interface. And sometimes a model can considerably improve by making a better assumption for initial conditions that nobody has measurements, rather than changing a plant rate in the model. It may not be the cultivar that is, oh, too much stress, we get low yields. It may be that you don't represent the system well with the surface residue. So we need to be absolutely certain that we are good with these parameters before we go to the next level and we touch the model.
Perfect. All right, with no further questions and only a few minutes left, and I don't know how many people need to end on the hour or can stay a little bit longer. Let's move on to the section 5, user support.
Okay, this is the fun part. This is for all the people participating in this workshop and beyond. This is some resources like questions that I get now is where you can ask the questions after the workshop. In the APSIM website, here is the URL. There is links to go to the GitHub. There are links to go to training manuals, to videos and documentation. So this is after this workshop, this is your support. And of course, you can find more. This is the starting points. Second one, very, very important. As you open the model and you go to the home, there is an example section. Please click over there and spend hours, I repeat, hours, learning through the simulations. That's the best manual. You can learn APSIM by viewing examples or running simulations better than reading the documentation. So that's my #1 suggestion. Go through the examples, and there are plenty. And this comes together with the model, and you can find it here in the example folder. Next one, there are many training courses. What I did today, it was a 2-hour session where I tried to cover lots of things. We run every year, every second week of June, a 3-day, 25-hour intense training course. And that's the website. You can go there and get more information and learn more about the past workshops that we run. And as I mentioned, is the introduction to APSIM, user interface, crop models and cultivars, climate change, exercises, water balance, nitrogen cycling, practical applications, decision support tools, calibration. So that it's a full 25-hour training, intense training. So that's another option. Some pictures from the event over there. This year we had to run 2 workshops because the demand it was quite high. We had nearly 45 participants, so we decided to split the room, to split the workshop and get it 2 classes. To me, what was really great was to see some of the students call me and say, look, my simulation, that was really great and made me really happy. The line is the model and the points are the measurement that the student had collected from the field. So it was really, really great, and it was a great event. Okay, so you have also this one, and this is my final slide, and I have also here my email in case that people have further questions for me. And I want to thank everyone for listening to me the last 2 hours, and happy to take more questions and stay a little longer if needed to go through some other ones.
Great, thank you so much. I did post at least some links to what I hope are the right things for the training in the chat, as well as the GitHub at the APSIM initiative. Everyone, if you can just give a quick round of applause, either in person or virtually, that would be amazing. And again, as another reminder, as you exit Zoom, please take a couple of minutes to answer the survey if you can. And if you are interested in further workshops or activities from AG2PI, please check out our website at ag2pi.org.